In this lecture, we will look at chemical formulas and percent compositions. Let's start right in by looking at the chemical formulas for two different compounds. The first compound under consideration is ascorbic acid. The formula for ascorbic acid is C6H8O6. This is the molecular formula. We could look and divide each of the subscripts on this compound by 2, obtaining C3H4O3. This would then be the lowest whole number ratio of the elements in the formula, and this would then be the empirical formula. As we look at the molecular formula, we realize that it contains 6 moles of carbon, 8 moles of hydrogen, and 6 moles of oxygen. If we go to the periodic table, we'll see that 1 mole of carbon has a mass of 12.0107 grams. Again, if we go to the periodic table, we'll see that 1 mole of hydrogen has a mass of 1.0079 grams. And again, if we go to the periodic table, we'll see that 1 mole of oxygen has a mass of 15.9994 grams. We see moles of carbon cancel with moles of carbon, giving us 72.0642 grams of carbon. Moles of hydrogen cancel with moles of hydrogen, giving us 8.0632 grams of hydrogen. And moles of oxygen cancel with moles of oxygen, giving us 95.9964 grams of oxygen. So within 1 mole of ascorbic acid, there are 6 moles of carbon, and these 6 moles of carbon have a mass of 72.0642 grams. Within 1 mole of ascorbic acid, there are 8 moles of hydrogen, and these 8 moles of hydrogen have a mass of 8.0632 grams. And within 1 mole of ascorbic acid, there are 6 moles of oxygen, and 6 moles of oxygen have a mass of 95.9964 grams. If we add the masses of the individual components of ascorbic acid, then we should get the mass of the whole of 1 mole of ascorbic acid. So 72.0642 grams plus 8.0632 grams plus 95.9964 grams equals 176.1238 grams. So 1 mole of ascorbic acid has a mass of 176.1238 grams. This is then the molar mass. So we shall say molar mass of ascorbic acid is 176.1238, and I will write grams per mole to show that this is the mass of 1 mole of ascorbic acid. But ascorbic acid is a molecule, so I can also say that 1 mole of ascorbic acid has a weight of 176.1238 grams, or put differently, the molecular weight of ascorbic acid is 176.1238 grams per mole. I used the formula for ascorbic acid to obtain this mass, so I can also say the formula weight is 176.1238 grams per mole. Let's compare this with the compound sodium acetate. The formula for sodium acetate is NaC2H4O2. This is the formula, but not the molecular formula for sodium acetate. Why do I say this? If we have a compound that has a group 1 metal, then that group 1 metal will have a +1 charge. So the group 1 metals are lithium, sodium, potassium, rubidium, cesium, and francium. And what I'm saying is, if the compound contains lithium, sodium, potassium, rubidium, cesium, or francium, then that compound is an ionic compound because that group 1 metal will have a +1 charge. If we have a compound that has a group 2 metal, beryllium, magnesium, calcium, strontium, barium, or radium, then that group 2 metal will have a +2 charge, and that compound will be an ionic compound. So bear in mind, if we find a chemical formula that has either a group 1 or a group 2 metal in the formula, then that compound is an ionic compound. So we come over here and we look at sodium acetate and we see that it has sodium, and therefore it is clearly an ionic compound. So I cannot call this the molecular formula because this is not a molecular compound. This is an ionic compound. So we shall simply say that NaC2H4O2 is the formula for sodium acetate. Now this also represents the lowest whole number ratios of the elements in a compound. I cannot divide the 1 for sodium by a number and have it work out to be an integer value. So this is the chemical formula, and this is also the empirical formula for sodium acetate. We look at this and we see that in the chemical formula there is 1 mole of sodium. And if we go to the periodic table, we shall find that 1 mole of sodium has a mass of 22.98977 grams. Moles cancel with moles, and we have 22.98977 grams of sodium in our 1 mole of sodium acetate. We see in our formula we have 2 moles of carbon, and if we went to the periodic table, we'd see 1 mole of carbon has a mass of 12.0107 grams. This means that 1 mole of sodium acetate contains 24.0214 grams of carbon. In our formula for sodium acetate, there are 4 moles of hydrogen. If we went to the periodic table, we'd see 1 mole of hydrogen has a mass of 1.0079 grams. Moles of hydrogen cancel with moles of hydrogen, and 1 mole of sodium acetate contains 4.0316 grams of hydrogen. The formula has 2 moles of oxygen, and if we went to the periodic table, we'd see that 1 mole of oxygen has a mass of 15.9994 grams. Moles of oxygen cancel with moles of oxygen, and 1 mole of sodium acetate contains 31.9988 grams of oxygen. So these are the masses of the individual components in 1 mole of sodium acetate. I will add the masses of the individual components, and that will get me the mass of the whole, and this works out to be 83.0416 grams. So I can certainly say that the molar mass of sodium acetate is 83.0416, and what this means is 1 mole of sodium acetate has a mass of 83.0416 grams. I cannot use the term molecular weight. Not with sodium acetate, because sodium acetate is not a molecule. It is an ionic compound. I can use the term formula weight because I used the chemical formula to obtain this mass. So we've obtained the molar mass, or the formula weight, for ascorbic acid. The question we pose now is, what is the percent composition by mass of ascorbic acid? Again, we know the formula for ascorbic acid is C6H8O6. And what we're saying is, okay, there's got to be some mass of carbon in a certain amount of ascorbic acid, some mass of hydrogen in a certain amount of ascorbic acid, and a certain mass of oxygen in a certain amount of ascorbic acid. What are the percentages? If we added up the individual masses, we should get to 100%. And what we're saying is, well, what would the percentages work out to be? Remember, percent equals the part divided by the whole times 100. We'll look here and we'll say, all right, we have C6H8O6. And we must think of, in this case, the 6 representing the moles of carbon, the 8 representing the moles of hydrogen, and the 6 representing the moles of oxygen. We shall assume there is one mole of C6H8O6, or put differently, we shall assume that there is 1 mole of ascorbic acid. All right, so when we want our percent composition, we shall say we want the percent composition of carbon. The percent composition of carbon will equal the mass of carbon divided by the total mass, or the whole, times 100. The percent of hydrogen will equal the mass of hydrogen divided by the total mass, or the whole, times 100. And the percent oxygen will equal the mass of oxygen divided by the total mass times 100. Well, we said we shall assume that we have 1 mole of C6H8O6. We just determined the molar mass of ascorbic acid, and we said the molar mass of ascorbic acid was 176.1238 grams. This means that if we have 1 mole of ascorbic acid, there is a mass of 176.1238 grams. Since we assume there's 1 mole, this means that there are 176.1238 grams of C6H8O6. Let's look at the percent carbon by mass. And we are saying by mass, so our units of the part and our units of the whole must be in grams. When we looked at ascorbic acid previously, we determined that 1 mole of ascorbic acid contained 72.0642 grams of carbon. So our percent carbon will be 72.0642 grams of carbon divided by 176.1238 grams of ascorbic acid times 100. And this works out to be 40.917% carbon. Again, we're assuming that we have 1 mole of ascorbic acid, and we are also saying that we have 8 moles of hydrogen. 1 mole of ascorbic acid contains 8 moles of hydrogen, and 8 moles of hydrogen has a mass of 8.0632 grams. So our percent hydrogen will be 8.0632 grams divided by the whole, which remains 176.1238 grams. We will multiply by 100, and this gets us 4.578% hydrogen. Again, we are assuming 1 mole of ascorbic acid. We are now interested in the percent composition of oxygen. When we looked at 1 mole of ascorbic acid, we saw that it had 6 moles of oxygen, and 6 moles of oxygen has a mass of 95.9964 grams. We'll take the 95.9964 grams, divide by 176.1238 grams, and multiply by 100. And this works out to be 54.505% oxygen. So, the percent composition by mass of carbon in ascorbic acid is 40.917%. The percent composition by mass of hydrogen in ascorbic acid is 4.578%, and the percent composition of oxygen in ascorbic acid is 54.505%. Let's consider a compound that contains only carbon and nitrogen. So we'll look at this and say, well, we have carbon and nitrogen, and we want to know what the empirical formula is for this compound. So we can think of this and say, well, I'll put CX and NY. And we say, well, what do X and Y represent? Well, X represents the number of carbon atoms and Y represents the number of nitrogen atoms. That's good, but hopefully you're seeing we don't think of chemical formulas entirely in terms of atoms. We also think of the formulas in terms of moles. So in this case, we shall say that X represents the number of moles of carbon and Y represents the number of moles of nitrogen. Let's say we have some sample of this carbon-nitrogen containing compound. We take our carbon and nitrogen containing sample, we put it on a balance, and we determine the mass of the sample as 8.3258 grams. From there, we do analysis on the sample, and we determine the mass of carbon and nitrogen in the sample. And in this case, perhaps we ascertain that this 8.3258 gram sample contains 3.2588 grams of carbon, and it contains 5.0671 grams of nitrogen. So we have 8.3258 grams of sample, and we have the individual masses of the carbon and nitrogen that are in that sample. We could certainly ask the question, well, what is the percent composition by mass of carbon and nitrogen in the sample? And again, we will be looking at part over whole times 100. Now, in this case, we're told percent composition by mass, and so we have the masses of the parts and we have the mass of the whole. So we shall say the percent carbon in this sample will be 3.2588 grams, and this was of carbon, divided by 8.3258 grams times 100. And this works out to be 39.141% carbon. We could look at the percent nitrogen, and again, it will be part over whole. The part will be the 5.0671 grams divided by the whole, which is still 8.3258 grams, multiplied by 100, and this works out to 60.860%, and this is percent nitrogen. We can take our data and glean more information. We said that we have C, X, and Y, and we know that X and Y represent moles of carbon and moles of nitrogen. With the knowledge of the masses of the individual components, in other words, the mass of carbon and the mass of nitrogen, we can determine the empirical formula. Our strategy is fairly straightforward. We're going to take the mass of carbon and convert it to moles of carbon. We're going to take the mass of nitrogen and convert it to moles of nitrogen. Well, we'll just fill in the moles of nitrogen in our subscripts and ensure that they are the lowest whole number ratios, and then we'll have our empirical formula. So the question is, what is the empirical formula of the compound in our sample? Well, we'll say that we have 3.2588 grams of carbon. Again, we go to the periodic table. We see that 1 mole of carbon has a mass of 12.0107 grams. Grams cancel with grams, and this gets us 0.27132 moles of carbon. We know that we have 5.0671 grams of nitrogen. We go to the periodic table. We see that 1 mole of nitrogen has a mass of 14.0067 grams. Grams of nitrogen cancel with grams of nitrogen, and this works out to be 0.36176 moles of nitrogen. We shall then say this is our value for X and this is our value for Y. So our empirical formula we determine by writing C 0.27132 and N 0.36176. So we are saying that X and Y, the subscripts in our formula, represent the moles of carbon and nitrogen. These are not whole numbers, but the way to make a non-integer value into an integer is to divide it by itself. So I will come over here and divide 0.27132 by 0.27132. But if I divide this number by that number, then I must also divide this number by the same number. So we see now we have C1 and N 1.333 repeating. Well, the 1 certainly is a whole number, but 1.333 is not a whole number. So I shall multiply each of the subscripts by 3. So I put parentheses around my chemical formula, and this 3 means I multiply the 1 by 3, and I multiply the 1.333 by 3. And so the empirical formula works out to be C3N4. So if we know the total mass of the sample, and we know the masses of the elements within the sample, we are able to determine the percent composition by mass, and we are also able to determine the empirical formula. Let's consider a case where we know the percent composition by mass, and we are asked to determine the empirical formula. Let's say our compound contains 2 elements. One is osmium, its symbol is OS, and the other is oxygen. And we're told that the percent composition of osmium in our compound is 74.827%. And we're told the percent composition of oxygen in our compound is 25.173%. The question is, what is the empirical formula? In this case, we are going to assume that we have 100 grams total of compound. Why 100 grams total? Remember, when we're looking at percent composition, we are looking at percent composition by mass. So we are saying we have some mass that is the part and some mass that is the whole. So in this case, since we're working in percents, we'll just assume that the whole is 100. This is a reasonable assumption because if we look at our percentages add up to 100%. And we are looking at percent by mass, so we shall assume that we have 100 grams total. And again, percent is part over whole times 100. Well, if the whole is 100 grams, then the part must be 74.827 grams. So what we're going to do is say, well, this 74.827% translates to 74.827 grams. And this 25.173% translates to 25.173 grams. Well, we're looking for OS, X, and OY. And remember, X and Y in our formula represent moles of osmium and moles of oxygen, respectively. Well, we have mass of osmium and we have mass of oxygen. All we need to do is convert these masses to moles and plug them in for X and Y. We have 74.827 grams of osmium. We go to the periodic table and we see that 1 mole of osmium has a mass of 190.23 grams. Grams of osmium cancel with grams of osmium, and this works out to 0.39335 moles of osmium. We have 25.173 grams of oxygen. We go to the periodic table and we see that 1 mole of oxygen has a mass of 15.9994 grams. Grams of oxygen cancel with grams of oxygen, and this gets us 1.5734 moles of oxygen. This is our value for X. This is our value for Y. We shall write OS 0.39335 and O 1.5734. And again, we want the empirical formula, and the empirical formula is the lowest whole number ratios of the elements in a chemical formula. This is not a whole number, and this is not a whole number, but the easiest way to make this number a whole number is to divide by itself. But if we divide this number by that number, then we must divide this number by that number as well. This gives us OS 104. So the empirical formula for our compound is OSO4. Let's consider another problem. Again, we're going to say that we have some sample, and this sample has come into the lab. And in this case, we know that the sample contains three elements: carbon, hydrogen, and oxygen. We weigh this sample on a balance, and we determine that the sample has a total mass of 13.190 gram sample. And again, this sample contains carbon, hydrogen, and oxygen. We do some further chemical analysis on a sample to determine the mass of carbon in a sample, the mass of hydrogen in a sample, and the mass of oxygen in a sample. And again, the masses of the individual components should add up to the mass of the whole. And in this case, we determine that there are 5.4594 grams of carbon. There are 0.4581 grams of hydrogen, and there are 7.2745 grams of oxygen in the sample. We have two questions we're going to ask. First, what is the percent composition by mass? And then we're going to determine the empirical formula. So the first question: what is the percent composition by mass of carbon, hydrogen, and oxygen? Again, percent is part over whole. We have the part, we have the whole. We have the part, we have the whole. We have the part, we have the whole. So our percent composition for carbon will be 5.4594 grams divided by 13.190 grams times 100. This works out to be 41.390% carbon. For hydrogen, we have 0.4581 grams of hydrogen divided by 13.190 grams total, and this will be times 100. I'll erase the hydrogen here just to be consistent. I didn't write it up here. And this works out to be 3.473% hydrogen. And for oxygen, we have 7.2745 grams of oxygen divided by 13.190 grams total times 100. And this works out to 55.152% oxygen. So our compound is composed of 41.390% carbon, 3.473% hydrogen, and 55.152% oxygen by mass. The next question is: What is the empirical formula? Well, we can think of this as CXHYOZ. And X is the number of moles of carbon, Y is the number of moles of hydrogen, and Z is the number of moles of oxygen. We have in our sample the number of grams of carbon, the number of grams of hydrogen, and the number of grams of oxygen. We shall convert these grams to moles and plug these moles into our chemical formula. So we shall say that we have 5.4594 grams of carbon. We go to the periodic table and we see 1 mole of carbon has a mass of 12.0107 grams. And we see that grams of carbon cancel with grams of carbon. This gives us 0.4545 moles of carbon. We see that there are 0.4581 grams of hydrogen. We go to the periodic table. We see that 1 mole of hydrogen has a mass of 1.0079 grams. We cancel grams of hydrogen with grams of hydrogen, and this gets us 0.4545 moles of hydrogen. We see that there are 7.2745 grams of oxygen in our sample. The periodic table tells us 1 mole of oxygen has a mass of 15.9994 grams. Grams of oxygen cancel with grams of oxygen, and this gets us 0.4547 moles of oxygen. So our formula is C0.4545, H 0.4545, and O 0.4547. We'll divide this by 0.4545, this by 0.4545, and this by 0.4545. And so our empirical formula is C1H1O1. We will continue our examination of this compound, specifically this compound with an empirical formula of C1H1O1. Sometimes the molecular formula and the empirical formula are the same thing, but oftentimes they're not. Now we look at this formula and we see that it's C1H1O1 for the empirical formula. Could the molecular formula be C2H2O2, C3H3O3, C4H4O4, C5H5O5? It could be. We need another piece of information, and that is the total number of moles that was in our sample. Now, in the lab, we have different analytical techniques, and there are ways to determine the total number of moles in our sample. So in this case, we shall continue on with our consideration, and we shall say, well, we had a 13.190 gram sample, and let's say we do some analysis on a sample, and we see that the sample contains 0.2273 moles. And this will be moles of substance. The logical question is, what is the molecular formula? We ascertained that the empirical formula was C1H1O1. So we could work this the long route, and we'll do so here. We would say that we have 1 mole of carbon, 1 mole of hydrogen, and 1 mole of oxygen. And again, we'd go to the periodic table. obtain the masses of each of the elements. And use these to obtain the molar mass, which is 29.018 grams per mole. Now, this is the molar mass of the empirical formula. And the question is this the same based off of the information we were given? In this case, let dimensional analysis drive your thinking. Ask yourself, well, what is molar mass as far as its units? Well, it's the number of grams of some substance in 1 mole of that substance. So we're going to say grams per mole. Can we look at the number of grams of the sample and the number of moles of sample? Yes, we can. We see that we have 13.190 grams of sample and we have 0.2273 moles of substance. So our sample contains 0.2273 moles. So we can say that the molar mass of the sample is 13.190 grams over 0.2273 moles. And this works out to be 58.029 grams per mole. Well, we look at the molar mass for the formula CHO, and we realize the molar mass for the formula CHO is 29.018 grams per mole, but the actual molar mass of our sample is 58.029 grams per mole. We said then that the other possibilities were C2H2O2, C3H3O3, C4H4O4. Let's try C2H2O2. In this case, we would have 2 moles of carbon And again, this gives us a molar mass of 58.036 grams per mole. Well, this matches what we obtained based off of the mass of the sample and the number of moles in that mass. So, because C2H2O2 as a molar mass or as a formula weight matches the molar mass of the sample, the molecular formula is C2H2O2. If we multiply each of these subscripts by 2, then we should be doubling the mass of the formula. And this is a doubled mass of the formula, and so we did not actually need to go through this computation to determine this. We could have, again, easily just multiplied that by 2. I worked it out the long way to help illustrate the point. So in this case, we have the empirical formula, and the molecular formula. In this lecture, we have examined chemical formulas as well as percent composition, and we have looked at the relationship between percent composition and chemical formulas. Ensure you're able to do the calculations that were covered in this lecture. You will need such skills in your further chemical studies.